continuing with material for homework 2, 3, 4, etc. And before that, any questions? Getting to submit. Question about yeah.
I submitted homework 1 in Python. Hope that's okay. If you have issues with that.
Not about the Python itself, as long as you're doing things legally, every bit go through this matrix, and it's all documented. I hope that I'll figure out. If not, I'll get back to you. And if you also can submit a video or a few screenshots that shows that you did. Oh. So I had a comment. Thanks for the people that answered for the questionnaire that I asked you to answer. I'm going through a lot of linear algebra. Some of it, I don't think that somebody that doesn't know any linear algebra can get it only from this course, but if you have seen it a few years ago, I'm trying just to remind you. Yeah, and people on Zoom, can you hear me? Good. And the chat is, you see the chat, so see the chat. So yes, if you have any questions. Okay, so last things that we study is that if we have a ray and we have a sphere, where does this ray hit the sphere? Where does the ray hit the sphere? Question?
Yeah, we were just looking at like which material this slides upon.
Is that the lecture is called Lecture 8.
Lecture 8.
Yeah, I just might not update it.
Oh, yeah, I have. Sure. Lecture 8.
No, let's make sure that you have the very, very latest version. Give me some. Okay, if you click, if you refresh. We studied how to find the intersection point of a sphere with a ray, which essentially gives us a little quadratic equation where t is unknown, and then t has an imaginary solution, which means that our ray misses the sphere completely, or it might have two times, which means the first intersection point and then the later intersection point, because the ray has time associated with this, or one intersection point, which just means it's tangent. Both solutions are the same. Let's talk about a projection of orthogonal projection of a point P. As always, I have some ray. Here is the ray going on. So the ray is given by the point O, and I give it some direction D. I don't care very much about D. What I care is about V prime that doesn't move, but this V prime that you can see over here that is a normalized vector to this direction. As usual, the same treatment that we give all the ray. There is a source of the ray, and then there is the some vector to get the direction. We have the vector V. And in addition, in this case, I have a point P, which might or might not be on the ray itself. And what I want to ask is, along this way, what is the nearest point to P? Which point along the way is the closest to P? And I can solve it in two different ways. I can think about this fly that moves on the way, starts at O1, and as the time progressed, this fly, called it R, move along the way, R4 fly, and look at the angle that I define over here. This angle that is defined from going from O1 to the point R is parameterized by times, depending on the time, and then going to this other point P. And what happens when T is moving? Then, of course, this angle changes, started from maximum angle and going all the way, getting smaller and smaller and smaller. And at some point, of course, it's becoming 90 degrees. Starting there, it used to be larger, now it's smaller. At this point, it's 90 degrees, which means that going from O1 to P, go from O1 to R and then to P, it's a 90 degrees angle, which also means that R at this moment, it's as close to P as it will ever get, as long as it's confined to move on the way. But so what should happen at this point is that it's this vector V times what's happened with. I want that the vector V will be orthogonal, because at this time it's orthogonal to the vector that goes from P to R. This should be orthogonal to this, or V times, it's V plus something, but V is a vector, it's direction, it doesn't care where it's origin. So V times what is O1 plus T0, because I don't know what is T0, but when it will happen, then what is this point? O1 plus T0 minus P, it's a vector that goes from this direction, actually downward, rather than upward, doesn't matter. I could have also gone from O0 plus TV0 plus P, this P minus this guy, should be 90 degrees, or as usual, V times T0V, V times T0V. Let's move it to the other side, so it's with minus T0. T0 is the time that it's as close as possible. V times V equals to this constant that you're getting here, because V is a vector, O1 and P are vectors. So we're getting that T0 is P minus O1, P minus O1 times V. Wait, what happened with the V that times V that appears here? Well, V is unit length for convenience. So that's the time that it will happen. And then I can find the exact time via just take O0, O1 plus T times, T0 times. So that's the orthogonal projection. You'll use it a lot in homework too. Another way to think about the orthogonal projection is also to say, let's connect a vector from O1 to P, that is P minus O1. Think about this direction, what happens here. That's just an orthogonal projection. I want to ask what is the length of all this guy? What will be the length of this guy? If I project it, what will be this length? And we know how to project one vector onto another one, right? So I have shown this example multiple times. If this is a point P and this is a x vector, x which is 1, 0, then the distance over here is just the x vector times P. And if I take this number and now multiply by the x vector, it will also give me this point. Same goes here. Look at the vector P times O, dot product V. V is just an x vector, just differently oriented. and that gives you the length of the projection, which means, again, because V is moving in units, 1 meter per second, its unit length, then once I know the length of the orthogonal projection, finding the point with the orthogonal projection would be take this new vector that I just created, P minus O1, project it on the unit vector. V1, give you the length, that's T0. Okay, two ways to get to the same conclusion. I showed you, I think that's the only difference in the slide. I showed you, now in the slide there is also an example of the input, the JSON file. Input to homework 1, homework 2, sorry. In this JSON file, I'm asking you to find intersections of rays and billboards. And to find intersection point of ray with billboard, I can actually have this kind of discussion. I want to ask what is the, I want to ask, we like to represent this plane as find the normal vector to the plane, which I don't give you in the input, but once you find the normal vector to this plane, then look at all the point P such that P times the normal vector equals A is one of the points on the plane, no matter which, times the normal vector. We saw the same thing at the beginning of this set of slides. We talked about it in a line, the same goes for a plane. If you don't believe me, go to GeoGebra and just type XYZ times the normal vector equals 0, will give you a plane that goes through 0, 0, and normalize. And the proof, we saw it on a line, the very same proof. Look at any two points, say Q and A. If they are both on the plane, then their dot product by n should be 0. And if A times n equals P times n, then the gap between them equals 0. I'm scanning through it because it's word by word what we had to develop the point for a line. But there is something new. I didn't give you the unit vector, the normal. What I gave you for every billboard were the 3 corners of the billboard. The lower left, lower right, the upper left, upper right, lower left. How do you generate? Now you need to find where a ray hits this plane, which implies I need to find the normal. How can I do it? Well, I have the 3 corners. Let's take from one corner the 2 vectors that connect it to the other corners. From one corner of the billboard, look at the 2 vectors that connect it to the other corner of the vector, say P minus A. That would be P minus A will be one of the vectors. Q minus A will be another one. What do we know about cross product? Cross product produces a vector that is orthogonal to both. So you want to say here is my billboard, and I will generate a normal vector by specifying the P lower left minus P lower right. That would be one possible vector, and P P lower right minus P lower left, and P upper left minus P lower left. These will be 2 vectors that you play with. Remember? P, lower left, lower right, upper left, and upper right, just without the P. I didn't tell you the coordinates. In the file, I don't give you the coordinates of the lower right. I just give you the other three. How do you calculate them? Oh, from all of this, how do I calculate them?
Take the coordinate of the lower right and translate it by the vector.
I prefer just to start from the lower left, actually. So I'll go from the lower left. I want to go to this one. So, but sorry, I interrupted.
Yeah, then you will take the other 2 points. That will give you the translation vector, and then you just add it to the coordinate of the lower left.
Look at this vector, which is what? Upper left minus upper right. Upper left minus upper right. Take this vector and start over here. So have lower left plus, let's write it nicely. Again, lower left plus upper left minus upper right. That is equals to lower right. Everybody agrees? That this walking distance from here to here, had I started from here, it will take me to the lower right. Because once again, the billboards are always nice rectangles. And it doesn't matter how they are arranged in three, they're still rectangles. Okay, by the way, there is a difference in the way that it's presented between this and the way that I described homework 2 last year. So there is a small difference, but it's enough to help me find, it's not the reason that I had this difference, but there is a difference if you're recycling code from last year. There is something that you either need to pay attention to or either figure out that you are recycling this code.
I have a quick question.
Yeah.
On homework 2, the JSON file you give us, are we assuming that the normal will be in the counter clockwise direction or something?
Fantastic question. Stay with this. So we discussed last time how to generate a factory of rays. How do we create this ray? We created the eyes, and we had the UVW, and then we put the image plane at distance d away from us, placing points on the image plane, and for each one of them, shoot away, and we want to retrieve the color. Now let's talk about how do I find the color of a point of the billboard that I hit. So I first need to find whether I hit the plane that contains the billboard. Again, I want to know where in the billboard my ray hits, if at all, or if it's missing. And to answer this question, I'll go by checking first, find the intersection point with a plane that contains a billboard. So here is how I suggest to do it. Our formula for the lower left, basically this one, you can write it in a few different ways. So you have the lower right. Now, from some application, it would be nice to normalize this vector. Sometimes I actually prefer not to normalize them. You see. For the normal, of course, the direction of the normal, it doesn't matter if the vectors are normalized or not. The direction is the same. And again, normal is terrible word because I can talk about a normal to a plane without arguing that the length is 1. So sometimes sort of rather than normalize, let's say, make it unit length. Maybe it's less confusing. Okay. U will be the vector from the lower left to the lower right. That will be the vector U connecting them, and U prime will be a unit vector in this direction. Not to be confused with the U of the camera coordinating system. This is something that is individual for this particular billboard, the different billboards. Each one will have its own U and U prime. Similarly, V is a vector, not necessarily unit, connecting the lower left to the upper left, that is upper left minus lower left. V prime is a unit length vector with the same legs, in the same direction. Just take U prime is take the vector U divided by the length. Now it has unit length. And now I want to define N prime, which is U prime cross V prime, or maybe I want minus of this vector. So if we are watching this plane, if we are watching this image, I want N to point toward U. So U times V or V cross U cross V or V cross U?
U cross.
From U to V. Again, thinking about the screw, going from U to V. That's how you know if the billboard finds failure. And you can always check if you hit the plane, but the vector is away from you, then you are seeing the back side of the billboard, decide about the default color, if you want. That the back side always have this color. Okay, and now you have U prime, you have V prime, they are unit length, and now you define normal vector, as we said, U prime cross product. V prime points toward U, and if this is 1 and this is 1, then N prime. You go check it. It's also unit length. Yes, question?
Yeah, I have a question. So from earlier you asked the question from U to V, is that like the clockwise? No, that's the counterclockwise, right? Sorry, I'm just making sure of the direction, like to find the...
In this case, V is counterclockwise to U. V is counterclockwise to U, and again, some people would prefer this, some people prefer this. I like to think about it as if I'm placing a screw over here and I'm rotating it always along the shorter angle between the two vectors, from the first to the second, in the shorter one, when the screw comes to me, that is, which in a sense unscrewing it, or V cross U going clockwise will make the screw going to the opposite direction. So to have the normal pointing towards the viewer, that's a formula. Okay, so I didn't have to normalize to create U prime and V prime, but it will be convenient next. So far, we know how to compute the intersection point of the ray, every ray, we had it in the last class, with this plane that I just created. I didn't say it, but what will be the formula of this plane? I have the normal, all the points x in the plane, x vector, that is x, y, z, such that x, y, z times dot product, the normal, n, equal n times pick any of the 4 corners, they'll all give you the same value. This is a formula of the plane. Now you have a ray. You can find the time that the ray hits this plane. If it's negative, then the plane is behind you. If it's positive, then you found the intersection point. How do you find the intersection point? You take the time times the direction that the ray moved to, plus the I where you started, and you're all good. I'll show you a trick at the end how we can assume that the I is actually in 0, 0, 0, but that's a trick that will suggest an alternative way. Now, if my point Q hit the ray, it's possible that this intersection point is what the heck? Maybe it wants me to log into, excuse me. Okay, so it's not about logging in. Oh, because I set it as private, that's why it's so upset. Okay, so we have the point Q. We have the point Q. Q is an intersection point where the ray and this whole image. And I want to ask first, is this inside the image or not? And if it is inside, that is it inside the billboard? And if it is inside the billboard, I need to know at which pixel it is. But the ij of the pixel, because I'm just copying the color, the RGB value of this pixel. So here is Q, as you've seen before. In this case, U and V, for convenience, are just the X and Y direction. And I want to compute a value alpha. A value alpha, which I'll define as follows. Alpha is F. What is F? I'll take Q and I'll connect it to the lower left corner. F is this vector from the lower left corner to Q. That's F. Take F multiplied by U prime. U prime, remind you, is U just normalized, just like the X vector over here, multiplied by 1 over U without the prime, which is, what is 1 minus U in this case? It's 6, the distance from here to here. That's what I suggest to alpha to be. So what's happening here? F times U is just a projection, orthogonal projection on U, which happens to be 7 in this case. Q, which is Q is outside the image. And now I divide it by the length of the lower edge, X, and that would be alpha. Alpha in this case, 1.7. Let's prove something proved by examples. Let's take Q and move it to at least that its X pen is inside the image, and alpha now is 0.9. Why? Because the projection is smaller than the distance from the left corner to the right corner. So I proved by example that a necessary but not sufficient condition for Q to be inside the image is that this expression alpha should be smaller than 1. Agree? No matter what u was, as long as, no matter if the upper left, can I move it? It's the other part. It doesn't need to be orthogonal to the x or y. U and v don't have to be in any particular coordinate system. They just need to be orthonormal. If alpha, this expression over here, is larger than 1, then the ray misses the billboard. It hits a plane that contains a billboard, but it misses the billboard itself. It's to the right of the billboard. Similarly, having the same instruction, but now alpha is negative, telling you, yeah, it's also it's also sufficient to declare that Q is outside the billboard. Okay, so the pixel is inside the billboard only if alpha is between 0 and 1, which is once again only a necessary and not sufficient condition. So let's define beta as f dot product v prime. V prime, I remind you, unit length, times 1 over the length of v. V, the length from here to here, 3 in this case. Had it not been dividing it, like, if I'll just look at this part, then I'm just getting the projection of Q on the y-axis. What's the length? I divide it so I'm getting it, but in relative term, so that I'm at 0, 0 in the lower left, and I'm at 0, 1 at the upper right, upper left. And 1, 1 would be and when I'm here, alpha will be 1 and beta will be 1. So again, alpha and beta on the board, alpha and beta are 0, 0 in the lower left corner. Alpha and beta are 1 in the upper right corner. And if either alpha or beta are larger than 1, then you declare you missed the billboard. So that's one reason why I wanted to use is alpha and beta, but it goes further than this. Right? You see where it's going. So the same deal over here. Here is Q, connecting Q to the lower left by a vector called F. Compute alpha, which gives me kind of the normalized x coordinate. It's normalized because if alpha is between 0 and 1, then Q is somewhere on the x projection of the image, x, but whatever the x, the horizontal side of the image. And if alpha is either larger than 1 or smaller than 0, then you declare, hey, you're outside the image. And beta defines right here. Beta, analogously, f times v divided by the length of v, is also between 0 and 1. And it's independent of what the size of the billboard. Some of the billboards are huge, some are very small. Doesn't matter. It's uniform coordinates. And you see why I prefer to work with the alpha and beta, because now I can use what you did in homework 1, take this alpha and beta and convert it directly into each billboard has different number of rows and columns maybe, but if I'll take this point as a pixel or as j equal 1 and this point as j equals the maximum number of pixels, or do a singular transformation that will move alpha from B between 0 and 1 to between -1 and 1, basically doubling it -1, then you're just getting a multiply by nx, then you're just getting the number of pixels. Make sense? Let's see if I can get it right the first time, that J, if you're looking at pixel ij, then J would be, let's do it right, 2 alpha minus 1, I believe, times nx. Am I right? I'm making alpha, I want, when alpha is half, I need to be at 0, 0. When both alpha and beta are half, then you're taking the pixel that is in the middle of the bunny. So is my math correct? It's nx, alpha is between 0 and 1. Oh, so if you don't want to multiply, if you don't want to move in homework 1, I suggested to you to use parameterization of the images between -1 and 1. Here you can use it, or you can skip this chair point, and then J is nothing but alpha times nx. The nx would be the number of columns in the image, or the width. And beta will give you the height, the y. Cool, and that's all the math that you need. Questions about it? Make sense to everybody?
I have a question.
Sure.
So when we transform the billboard, if we ever transform the billboard, how do we update our UV coordinates? Because I know that like you apply the transformation to the UV coordinates, but can you do a change of basis on the transformation itself to get the transformation on the UVs automatically?
I didn't think about it. There is a different transformation that I'm about to describe that talks about the UVW of the camera itself. For the, oh, you're asking between the -1 and 1 to the 0, 1?
What I'm saying is when the billboard moves, do you apply the transformation to the original coordinates of the billboard to update the U and V, or do you do a change of basis on the transformation itself?
I did do a change of coordinates, but I prefer not to call it this way. It's a bit, would be overkilling here. Okay. It's really, yeah, I express, I take the billboard, I think about U and V as X and Y, and now the meeting point is expressed as U as alpha and beta. You some amount of U, sometimes of V, and tell you how to get to the intersection point. Go to the lower left corner on your part, plus alpha times U plus beta times V. Alpha times U, no, without the prime, but alpha times U without the prime, so when alpha is 1, you make it all the way to the right side. Or alternatively, alpha times the length of U times lower left plus alpha times number of pixels times the U prime direction, either way. I think that the first one was simpler. Okay, and I think that you know everything that there is about homework 9. I'll show you one more trick. So we discussed the case before I start with, just to summarize, you know how to create rays, you know how to create camera coordinates, you know how to generate pixels, you know how to find if array hits a plane, you know how to find if array hits a billboard. Once array hits a billboard, you are using our notion of orthogonal projection on the UNV direction to find your own coordinates in the billboard own coordinates, and then you convert it into the pixel inside this image. And I think that's all you need for this homework. And of course, stuff that we'll do later would be asking, hey, if this point that I just hit, if its transparency is 0, if it's transparent, then I'll keep on with this way. Or essentially, I don't keep on with the array. I find all the intersection points of the array with all the billboards, and I just find the smallest time for which I hit a pixel that is opaque. So that's one of the things that it's going next. Yeah.
A week, maybe 2 ago, you showed us NERF. NERF, does its ray casting and all that stuff, but you're using a learned function to find its color and density via NERF at every single point. So does that get around the issue of having to kind of sort of know beforehand what the color and density is at the point when you get the point from the ray, so NERF is inherently learning it as opposed to you having to infer it?
I hope to be an expert towards the end of the course, especially if more people want to do about NERF. By the way, I have a small research position if you want to actually play with NERF and get money, because actually mining / landslide / rocks application. So if you like NERF, then I plan to dive a bit higher. But here is what my understanding so far is, that you are generating something that pretends to be an occupancy maps, what voxels are occupied, and also for each one, what is a color and something about the reflection. But how accurate is accuracy map? It's accurate in the sense that it's good to produce something that looks like the images that you fed in. It might be what's happening in geometry, but might be completely wrong.
Right, but so in this case, though, when you cast a ray and you hit a point that's not, I guess, in the plane of interest, so to speak, you just don't render that point, right? Because there's nothing there. Whereas in NERF, you're not inherently telling it not to render the point. It's just so learning that there is no color, there is no density.
So NERF at the end use the ray shooting algorithms that you are implementing. The ray shooting is exactly as you're implementing, plus the shadings that you'll implement in the next week. NERF is just about how I built the model. The later part, at least the classical NERF, is assuming that every piece is computed by using all these algorithms, except that it tells it, hey, I'm the machine and I do these algorithms better than you. All this shading and ray casting, you can avoid a lot of them, and a lot of the 3D reconstruction you can avoid. But the ray casting happens the same. You have the camera parameters, create the camera parameters, and so on. This part goes just as this part of the NERF is exactly as, it's just what's a model that I build. Do I actually need a description of every, like NERF, if you just showed NERF these two images where the green one hides the red, then it has no clue that this exists at all. And it could say that if you look at it on the side, it will argue nothing exists at this point. I haven't seen it, nothing exists. And if you decide that one specific image captures enough billboard-like, one single image could replace these two billboards because they look, say, close enough to each other, it will just say, hey, just this one exists, but the image is some combination of the two.
But inherently, nerf is inferring the density because it has based on how it learns that the object is dense, right? So therefore, light cannot pass through it.
Correct.
Whereas if we're doing it in this more so classical way, we know kind of beforehand that there is that this front object is opaque, so therefore, so that we don't want, right?
What?
Okay.
And exactly what's the image about it that a nerve.
Yeah.
So part of the reason that nerve is attractive is that it will end up, in most cases, with something that a neural network that's storing it just takes a few megabytes. Even though the model itself to really represent it is many gigabytes of data. So compression is one of the. So we are moving to lecture 9, but I want to show you a cute trick before. The animation doesn't work as smoothly as I want it to, but here you see the image plane, the camera, the image plane that you're creating, shooting vectors through it. And so we have everything ready. Just as before in an image, it is completely incomprehensible. But I have a question for you. You need to create the image plane after you generated the U and V and W that we had all this time. What happens if you already feel I'm convenient and absolutely fine as long as the image plane lies in the image plane? Remember this factory of pixels where I put points to show the pixels. Put the image plane always at a distance minus d from, not the camera plane, from the eye, from 0, 0, 0, go in the minus z direction, go in the minus z direction d, and you'll put the image plane right here, and I already have it, and I don't want to reconstruct it. Just because you are moving your camera elsewhere or looking at a different location, you want the camera to be here, that's the eye, and that's a few objects that I have over here. But I already assumed that the eye is at 0, 0, 0 and not here at 2, 3, 5. And that's the only difference, just that the eye is in a different location. The direction that you are looking at is a minus d, minus z, and everything else is the same. Can I recycle the fact that I already have the code? And remember, I have this eye, and in the correct place, I need to put the image plane. Now with the image plane that I place in some different place depending on the eye, I need to shoot a ray. And for this ray, I need to ask where do I hit this billboard. Can I use the fact that it's already constructed? But I don't want to recycle that. All constructed from scratch. In the homework, you need to build it as if it constructed from scratch, but actually, that's not how the graphical pipeline usually works. Graphical pipeline will assume that it's convenient for us to think that the eye is at 0, 0, 0 and look at the minus z. So for the direction, let's wait a second. But if it's only translation, how can you shoot the ray? That's one of my rays, R, which is the I, which is given to you, plus T times V, and you have to create V, again, depending on the point. And I need to ask which of the billboard it states. And you already have this mechanism to generate another ray, R prime, that will be over there, just translated from the original ray. want to recycle it, I want to translate the arrays, I don't want a new algorithm, and I definitely don't want to take all my objects that are there and move each one individually. There are way too many objects and will take tons of time. Instead, I'll have a little magic that will take this way and teleport it to be this way. What would be this magic that will be on the array? I'll create the matrix T, which would be what? 1, 1, 1. And here I'll put the coordinate of minus the I. And every time that I shoot the ray, either I'll apply the ray translated by actually the inverse of T, so take the ray and move the coordinates to the I from here. Right? Or every time that you are attempting to access an object, a triangle, you don't look at the vertices of the triangle itself. You look at the vertices of the triangle multiplied by T minus 1, which will take the object and move it in the corresponding direction. So for translation, it all makes sense. Right? If you have already the arrays generated automatically in hardware, and it will always start when they are here at 0, 0, 0, we can now take as an input any camera location, as long as the direction is correct, and just translate it, just apply a matrix that will always proceed every operation. I want to ask if R hits an object. I'm asking if R multiplied by the matrix hits this object. Or multiply if the original ray hits the object, where the object is the original one, multiplied by minus 1. So far, I assume that I just need translation. The size of the billboard, the size, sorry, of the image plane, its size of -1 to 1 times -1 to 1. So that would be easier to convince. That I told you when you're generating the image plane to use it. Okay, what about rotation? Well, rotation is, we know how to do rotate around the X, rotate around the Y, rotate about the Z. Do I need if here the eyes that they gave me have look at, that points to a very different direction, I need to rotate it, but rotate around something. Let's see if my animation worth anything. So rotation was easy. Take the eye and move it to the origin. Again, take the eye, move it to the origin, that's just translation. Hopefully in all this mess, you can see how the eye moved to 0, 0, 0. And by the way, I did not set the coordinates right, but in the XYZ plane, you want, how do we usually think about it? We have positive X, if your origin point to our right, positive Y going upward, and where the objects are in the minus Z direction. So Y is vertical. In GeoGebra, I assume. Another thing, you have a click that asks you what do you want as a vertical axis, the X, the Z, or the Y. In graphics, we'll assume that points on the image are X and Y, minus Z goes this way, and positive Z go beyond us. So here is a very nice trick. I also need to do rotation, because that possibly the XYZ the UVWs that I created don't align with the XYZ. So I need somehow to take, it works only for the image plane, but I need to take the image plane and rotate it somehow. Without animation, of course. Animation of rotation, by the way, is fast. That's why we talk about it as a topic by itself. It's not linear interpolation. But I want to compute a rotation transformation that will take UVW that is somewhere there, right? If my up vector points this way, then I hold the so that would be the image plane in the XYZ, image plane on the XYZ. That would be the image plane that you are getting from the input based on the look at I, U, and V, and so on. That could be rotated this way. And now I need to move it so it's aligned with this one, which implies both translations. So the center, so the eye is actually here, becomes the eye, which is behind the ball, but in the center. But the direction should be the same. And here is the trick here, and here is why your work of computing VU, VW is still fruitful and well needed. So you computed the vector U, which means you computed U in the XYZ coordinate system. And you computed the vector V, and you computed the vector W, all in the XYZ coordinate system. And I'll put these three vectors as three rows, and I'll call this matrix R. And I ask you, what happened to this matrix UVW when I multiply it by the vector U? It takes U is unit vector, so U times U equals 1. U times V, orthogonal to each other, should be 0. U times W, 0 as well. So this is just the X vector, unit X. So this matrix R, take U to X, R times V will be 0, 1, 0, because V times V is 1. And V times U and V times W 0. So this is a Y vector, unit vector in the Y direction. And R W is the Z. Which now I'll explain why I insisted that everything will be of linear, or will be right-hand coordinate system. That's why W points to your back. So it will be aligned with your back, otherwise no rotation will work. And this is a rotation to take us from what to what? It takes us from a point in that is expressed in the UVW coordinate system. If now I have a point alpha U plus beta V plus gamma W, that is, I express the point in the UVW coordinate system, the opposite of what you usually have. And you multiply R by this matrix. What did you get? R times alpha times U. It will be alpha RU plus beta RV plus gamma RW, which is, what did we say, alpha R times U, it's a X, beta RV is a Y, RW is a Z, alpha, beta, gamma. So I moved from the UVW coordinate system, rotated the point into the XYZ coordinate system. Let's get that, XYZ. What should I do if I do the opposite? Let me show you the matrix that does the opposite. You either compute the inverse, or you will write a new matrix where you will write U again, but now take the coordinates of U and write it like so. And here is V, and here is W, the same UVW that we had before. And as you can easily check, this matrix is the rotation in the opposite direction, r minus 1. So, but think about it. If I have this matrix, you have a point in the XYZ plane. You have a point alpha, beta, gamma in the XYZ plane. What does this matrix UVW times alpha, beta, gamma? You have a point in the XYZ plane, whose coordinates are alpha, beta, gamma. What are you getting in return? You're getting alpha U plus beta V plus gamma W. This is just the same point, XYZ, just rotated by the matrix R. So when you're computing rotational matrix, you rarely need to actually call cosine or sine or asking what is exactly the angle of the rotation. You just express one set of vectors in the coordinate system of another one. And then you multiply the translation by the rotation, and that's all you need. You prefer to have the image plane always so its center is on the minus z and is on the minus z, and its size is -1, you're all in fine. You can still use this piece of the code, especially if this piece of the code appears as a hardware piece, which is the case in all graphics hardware that we'll start to talk about the Z buffers. But that will wait a bit. I'll just start the slide and we'll answer your question. Oh yeah, because that's not what I need. Yeah. Question?
So is one way of calculating our plane intersection taking the change of coordinate matrix, multiplying it by the ray that we're looking at, and solving for t, where the third row multiplied with our x vector gets us 0? So checking for 0 in the third coordinate of the billboard system?
Then you need to do it per each billboard individually. Each billboard is in different orientation. So doable.
But not
I don't want to say if it's simple or not. Definitely doable. It actually makes perfect sense, and as a midterm question, it's a great question. Can I assume always that the billboards are on the billboard are orthogonal to the z-axis, so we are always looking, but once you orient the billboard from the input to be, so its normal is oriented with the z-axis, of course the camera moves to a different location. I mean, you cannot assume always that the normal of the billboard points toward the center of the billboard, and its normal points towards the viewer. That would be a wrong assumption for this homework. Okay, but you can, with this trick of matrix, you can always assume that each in a canonical place, and maybe it saves actually some calculation because then the time will be easy to calculate. So I see the logic. Okay, ray tracing algorithm, light source, shoot at a point, and it influences the illumination, influence the point that you see. So for each pixel, you can compute the viewing ray from the light source, see how it illuminates, and now affect the viewer. Or alternatively, you can first find what is a point visible to the viewer, and now ask, is this in the sun or is this in the shade? And what's the illumination effect, either way. Okay, and it's easier to do for each pixel in the image, compute the viewing ray, intersect the ray with the scene, compute the illumination at the intersection. That is, now you need to shoot a ray to the sun from the intersection point, and that affects the color, both RGB and intensity, at the point what you report to the pixel in the image. Okay, and we had it already intersect where the eye at the direction gives some team in and team out. That's a procedure that you need to have. The teaming is not very much important here, but and that will report both intersection point as well as the time. Teaming is not really important, but the same procedure will do recycle your code or build it so you can recycle it. So it's emerge either from the eye or it emerge from some point that is on the surface itself, surface that is visible to the viewer. This is a point visible to the viewer, and then I'm shooting the ray toward the sun, and I want to see is this in the shade or not. Either any of this object shading it or not. Okay, and you can recycle the code. Skip it now. You can recycle your code pretty much, so it's can. I didn't find it necessarily convenient, but if you have triangles and billboards and spheres and other items, you kind of JavaScript is the object-oriented part can say that a lot of the code could be recycled out of. So, okay, and let's talk about illumination and about shading. 4 minutes to start about it. So for each pixel, decided what's the object that the ray hits. It turns out that the ray hits the blue sphere. Does it look like a blue sphere? Not to me in particular. Why? Because of the lack of any shading. It looks like a blue disk just as well. So I want, but you still report it as blue. Why? Even if it's sphere, you still report it as blue in homework 2, because you can assume that it's only ambient light. If you want already to include all the shading effects, it's part of homework 3, go for it. Definitely, you could. And you'll enjoy your picture much more. Here is the big hint of why do we need shading. We have this picture. Recycle us from the 60s. You see the blue picture. You see this plastic blue thingy. No idea how does it look in 3D. Now I'll add diffuse shading. Diffuse shading takes into account what is the color of the object over here, what its ambient color. It takes into account now what is a normal to the light at this point. If a point right here, its normal points to the projection, to the projector, to the source of light, then it's highly illuminated, like this point here, this point here. If the normal of the surface itself, normal to the surface, points away from the light, it should be much darker. It barely gets any light. We will do the math on it. But now it looks three-dimensional-ish, but very, very plastic, computer 60s, Minecraft generated. Now we need to add as well the specular reflection. Specular shading will add these white spots, and the beauty of this white spot is that that's the first moment that you actually care where is the viewer in the game. Because if the viewer moves a bit, the diffuse shading doesn't care at all. The specular shading will care and will change the location and pattern of this specular spot. And here is a picture altogether, and you see what are these regions that get this whitish spot out of it. So our next topic is, let's see how to do diffuse shading. It's very easy. And specular shading that we are not doing exactly. We find a model that mimics and something that looks almost like the real physical thing, that at least can cheat most of the viewers. But specular shading go to much deeper and care very much about what texture do you have. It's metal. You can go much further than what I'm going to discuss about specular shading. But we'll see the basic way to mimic or to approximate specular shading, which is called Phong model. And by the way, Phong model will be one of the confusing terms of this course, like normals, because we will have Phong shading and we'll have Phong interpolation method, and there are two Fongs, the same guy, but two different algorithms, both called Phong. But, okay, thank you. Questions? Everybody good?
Were you at SIGGRAPH 2023?
I'm sorry?
Were you at SIGGRAPH?
I've never presented in SIGGRAPH.
Oh, you never had a picture?
It's going pretty good. I just
From time to time.
So
I have to manage the
It was stupid for my type. I was in Stanford. My office was just a
because I was using the muscle directory
stupidly insisted on my theory.
So
I have papers that has to do with data structure.
and I'm like, well, I'm gonna submit it.
Most I got a paper about how to compute the silhouette.
I'm pretty sure we can work together on that.
Data structure.
I'm ready for you,
You
433.
you were saying something about the
Really?
earlier deadline?
Oh, yeah, that's
You're
good.
doing nerve scales, right?
Okay.
Are you
I couldn't
guys
find
familiar
this.
with?
Yeah, I couldn't see anything around there.
No, that's all right. That's fine.
I'll pull it up.
Professor in mining that tries to ask you.
So I still don't know the midterm. It's not updated on there.
Oh, yeah.
Identifying
It's just probably it's not
work
updated or it's
changes
indicated
in
or
work
something.
and will be
I didn't find
work
that
slides.
note. The one that you showed, there was nothing out
Instability
there.
of
I think it
mind.
was
That is
updated
really,
last week.
Wait, which one?
and has a
Homework two,
component
right?
is
Yeah.
how it's used.
Are you familiar with
Yeah, you
Gaussian
said something about
sliding?
theory.
SIGGRAPH?
Oh, it's a
You
nine.
should look that
Okay.
up. You
Okay.
might find out.
It's a nine.
It's so NERF is a ray tracer by principle, right? Gaussian, and it's it's a neural method as well, so very time consuming in terms of optimization and whatnot. Gaussian splatting is inherently a
Oh, yeah.
rasterization method.
Before the deadline of the
But it's not neural. It is
Um,
an optimization approach, but it optimizes
the
a huge set of Gaussians. So basically for every object you would see, you fit
So finish the nine first.
you fit a Gaussian to pretty much a whole bunch of objects, and that is significantly faster in terms of optimization time, but it also works in terms of like PSID scores. It's significantly better than NERF as well. The inputs are a bit different. In NERF you have a field of images, whereas in Gaussian splatting, you use a field of images, but you use structure for motion to get sparse point clouds, and then you initialize your 3D Gaussians using covariances
20 page
based on this
for one
sparse point
question.
cloud images.
And
Then you do some fancy algorithm work to fit Gaussians to different parts of images based on whether or not it's overrepresented or underrepresented in different things
And the
like that.
other
But
questions are easy. I just have like
it's a very,
one
very cool
page,
method.
two
It's
pages.
currently,
like-
NERF's very popular right now,
I didn't know
but
what
Gaussian sliding has proven to be better. than
theory
NERF.
of computation.
Oh, okay.
It's a
573.
possibility. Yeah.
One of the
Kind of. It's higher level than whatever, so it's not easy. I can.
Oh, I don't know that. I'm sure that I don't know much about her.
Yeah, I don't know what the limit of. Just don't want to overwhelm anyone.
If you understood enough from this paper,
Reduce
so
that
how
content,
to
and I
do
don't
it
know which
could
one to
be-
remove.
I'd be happy to
So I have a lot of work there to make sure that the most correct parts are still there.
Oh yeah, well
and
I
get
plan
things
on
covered.
my research
Yeah.
group. We have paper
But
readings
yeah.
every Friday. This Friday I was
I'll do
actually
homework
presenting Gaussian
one
splatting.
of this
It's
class.
a
It will be
huge use of my program.
today or tomorrow.
Whatever I make for
Yeah,
that,
I just did the
happy
theory part. I just have to go over and check like if I did it correctly. I just roughly went over so I know what's going on.
Assume that
And
they
then
know what.
hand solved some stuff. have to start drafting it, and so that I'm confident that this is the answer. And then I'll start the programming. Programming, I think I won't start until Friday because I'm just going to focus on these two deadlines. I have two other deadlines tomorrow. That's it.
Yeah, I also want to make sure, because I can't tell if they're due like 11:59 or like what time they are due on the day.
I could,
So I
next
got
Wednesday might be better, just so I could.
I know you have
So let me give it,
homework
cause I get to go
next
to my
week,
research
that's a
group
lot.
this Friday.
Yeah.
Excited for
You know
See how it goes, see what kind of
like
questions
the
are actually
programming
formulated
part is
based
gonna
on,
be
the needs
a
for this
lot.
class.
And when you find out, just let me know.
I'm actually in the
But I'm
ECU
gonna rush,
department.
like, because I want to
with
finish
Professor
all that
Abhijit
work. I
Mapanovis.
just want to revisit and see
The
where
whole
I've done
reason
wrong.
that
Like,
we,
maybe that much is not required. I
had
don't know
such
if I'm doing it
interest
wrong or
into
right. But
practice is one of our projects right now.
yeah,
Called
it's not
generative novel view
easy.
synthesis.
I have to
We're
read the
trying to
couple of
do
other
some sort
and
of
watch the video again and again.
modality adaptation,
which one?
so like from RGB.
For this homework from
something
theory.
like
Oh,
SAR,
okay.
so
And then of
non-infrared,
course, even the
which
homework
is
one.
inherently
You have
a tough
questions
problem.
about homework one? Ask me. But for the
So
homework
the
two
method
part,
that we're
like if you
basing
want
off
me to
of
take
was
over
published a
some
year
more
ago at
responsibility or
ICCV.
something,
It's
if
called
that's helpful,
generative novel
you
view
can tell the
synthesis. So what
professor about
happens
it.
is
You can take the
you
maybe
get
if you find theory part easy.
3 images,
Right,
input
yeah.
images max.
I'm sure we can like, we
With
still
that,
want to
you
work together on
render-
it too. I want to
Yeah.
still do some of it.
You don't
Yeah,
render,
but
but you
five
produce
homework is
a latent
Yeah.
feature field, a 3-dimensional
I think they're
feature
mostly in the
volume.
beginning of the week.
Uh,
Like if we
with
work
the
like
feature
later in the week,
volume,
like
Late in
the
the week
library,
works
use
fine
that-
because I'm also working on
strategies
my
to get
research
a
work, so I'll
feature
be
image.
so like
You take that
in the middle of
feature
it
image,
because
now
that
you're
deadline
looking,
is
you're
end
not
of the
looking at
month.
colors, you're looking at like 16
And during the
dimensional
holidays,
vectors.
I plan to
You
visit
take the
my
feature
cousin.
image, you
I'm going
cat
to
some noise on
Virginia
it,
to
then you
visit my
feed that through a
cousin.
diffusion model.
Awesome.
And
I have a
diffusion
niece
model,
and
like
nephew
they're all the
there.
rage right now, they're really
They
good
have
at
this
denoising.
American accent like
Nerf
they're
produces a lot of noisy images
tons of
usually.
clips.
So the idea is you feed
And they
it through a
already
diffusion
have
model,
know all the
you get a
shortcuts, like
image, and you get a
BTW
really,
and
really
all.
nice
They're just
RGB
like
image
9
out
or
of it.
8.
In a novel view,
Oh my
it's a novel
gosh.
view. So there's a lot of view transformations
Yeah,
that take place.
my niece
It
is
builds
funny as
a lot on
Gosh,
the
it's
idea
in
of
spring break
pixel
or
nerf.
summer?
So
Spring
pixel
break,
nerf is just a
yeah.
step above
I just
nerf,
plan
and that was,
just go with
that
it.
came
It's been
from
fun. I didn't visit them in
or
like last 1 year or so.
22. Anju,
going
Anju
anywhere
is her
for
name, I
spring
forget
break?
exactly.
Sorry, what?
Are you going anywhere for spring break?
Probably just back to my parents' house. And
Where
then,
do they live?
just in Gilbert, which is like an hour and a half.
Alright, that's cool.
Pretty much near Phoenix.
Nice. Yeah. Oh yeah, that's cool.
Yeah.
Fine.
So yeah, pretty much just going there.
Yeah.
Hanging out.
Sure.
But
Alright. Keep me posted about homework too, but don't worry much about it.
Right.
It's fine.
See ya.
See you.
And you guys don't want to call? Okay, so I leave in 15 minutes.
So pixel nerf builds upon the ideas of nerf, but nerf, again, uses a lot of images, scene specific. Pixel nerf tries to circumvent that with few images and scene agnostic. But basically, you have a target image. Your target image is the novel view that you would like to eventually output. You shoot a bunch of rays through your target image. You query those rays through your feature volume, through 3D feature volume that came from some neural network encoder. Use viewing transforms to get those points in the view perspective or whatever your image points were. So now you have like some sort of interpolated point from your target view. You render based on those interpolated points. So now your rendered feature image is now in the target view.
Okay.
So and then you feed it through the diffusion model with some noise to get an output novel RGB view. If you have time to look it up on your computer right quick, because the figure it's quite.
No, I want to spend time and do it. Yeah, do send me the links and our YouTube's involved with this. I'm studying from lectures and from papers.
No, yeah, but
I'm sure I also was scratching my head about maybe giving one of the later projects in this homeworks in this course actually would be maybe about nerf, but I didn't thought about it. The part that algorithmically I care more is that I don't think that I'll have anything novel to say about nerf at any time, but I'm very curious on other geometric algorithms like starting from how fast can I find the next point of view, the best point of view, out of the next thing, like John Kennedy, the guy I'm working with. He had a project where he went to the colossal cave, and over there and the LiDAR scans for a bunch of points, but course, you can guess on static cave there is still tones that you don't see. Guesstimate what would be your, if you LiDAR part, really heavy LiDAR thing that takes time and pain to, what's the next, out of the first n-1 scans, what should be your next scan that is likely to resolve most uncertainties? Or where should I place guards given on there for how should I do, people are, I'm not a, people are doing navigation out of nerves despite like slums, you know. Yeah, so anything that involved the geometric objects, but taking into account that the geometry is very fuzzy and uncertain, that's what I found fascinating. Or in the case of John and Lensline, I think I've seen cracked between rocks, and I need to go with my drone. If I'm a drone, I need to go closer, but I also need to move across a crack, and maybe I've seen other cracks. So what's the best placement that I want to move to? Yeah, etc. That's the type of questions that I'm very curious about.
Yeah. So that's cool. I'd be happy to send you.